All right, guys, let's work our way through some of these examples. So we have been ordered to compute the domain for the following functions and provide our final responses in interval notation. So no x is less than 2. That would be negative infinity to 2 with parentheses. So we got a fraction. You cannot divide by 0. You cannot divide 0. Divide by 0. So we would say that looks good, except that the bottom can't be 0. X squared minus 5x plus 4 cannot be equal to 0. So you solve that equation to figure out what our domain issues would be. So this is certainly factorable. You do x times x is x squared. Hey, 4 times 1 adds up to 5, multiplies to 4. And since the middle's negative, they're both going to be negative. Quick factoring trick. And then so x cannot be equal to plus 1 to both sides, plus 4 to both sides. So all reals, and this is the symbol for all real numbers, except x can't be those two. Now it says interval notation is the way in which whoever made this document wants it. So what I'm going to do is say, let's start with negative infinity. That's a good place to start when all reals is involved. You can go all the way to 1, but you got to stop. You cannot include 1. Now we start again. Keep going until 4. You cannot include 4. That's what parentheses mean. And then you go 4 all the way to infinity. So this is interval notation. This is just whatever notation. That's it. Number 2, we've got the 4th root of x squared minus x minus 12. You're going to set the inside of the root greater than or equal to 0 because it must be greater than or equal to 0. And if you recall, when we did inequalities with quadratic structure, we found critical numbers, the places where it zeroed out. In this case, it looks like x squared minus x minus 12 is factorable. X times x gives me x squared. Let's see. Negative 4 plus 3 is negative 1, and it multiplies to give me negative 12. Now, the critical numbers are the zeros, the place where it equals 0. So 4 and negative 3 are both critical numbers. You now set up the intervals to test them. This is basically a review from chapter 1 of how to solve inequalities of quadratic structure. So step 2 is where you set up the intervals. Start at negative infinity, go all the way to negative 3. You want to bracket it because it has an equal to for the 0. Bracket. And then you go bracket negative 3 to 4, and then bracket 4 to infinity. The negative 3 and the 4, they're not the domain issues. So that's why I'm not putting parentheses around them. All right, you test a point that lives in that interval. So negative 4 lives here, 0 lives here, 5 lives there. And we're plugging it into basically this expression to see whether or not it is greater than or equal to 0, or if it's not greater than or equal to 0. So if I plug negative 4 in here, I get a negative times another negative. That's positive. That's good. That means that that's going to be a part of the place where the function can live. That's going to be a part of my domain. For 0, that'd give me a negative times a positive. No dice. And then 5 minus 4, 5 plus 3, both positive, which yields a positive value. So what we just accomplished there by solving that inequality is we determined what the function's domain was. We determined where it lived. It lives not in the middle, but on the ends. So your domain would be categorized as negative infinity to negative 3, and then 4 to infinity. And I guess, technically we should put a union symbol in there to make it legit. Yeah, you know what? Keep in mind too, here's sort of the algebraic approach to everything. There's another way of thinking about it. Think about the graph x squared minus x minus 12. You guys know what parabolas look like now. They're either a U-shaped opening upward or closing downward, or opening downward. This one clearly opens upward. So it's kind of like, if I can determine where the zeros are, negative 3 and 4, and I know it's opening upward, I kind of have a feel for where the parabola is greater than or equal to 0. It's basically saying, where's the parabola above the x-axis? Well, from negative infinity to negative 3, and then from 4 to infinity. So just keep in mind, that's in your back pocket now, that you can pull out whenever you need to have a reassurance of, okay, I think this is the answer. Oh yeah, that makes total sense when I think of what the graph looks like. I'll write this a little larger so you guys can see it better. Oh, what happens when I take an even root and I intermingle it with a fraction? Well, let's just set the parameters. We know that x minus 2 must be greater than or equal to 0 because everything under the even root, and it's just the top part of the fraction, must be positive, or greater than or equal to 0. We also know that the bottom cannot equal 0. You cannot divide by 0. So the spots where x forces a 0 on the bottom, those are not in our domain either. So this is simple enough where I can just say plus 2 to both sides. All right, x must be greater than or equal to 2. So at bare minimum, the domain is bracket 2 to infinity. Now, it's probably going to have some stops along the way wherever this actually equals 0. So what we can do here is we can factor out an x. We can factor 9 minus x squared, difference of perfect squares. 3 minus x, 3 plus x. And then this tells us that, yeah, this is a part of our domain, but we have to keep in mind that x can't be 0, and it can't be negative 3, and it can't be positive 3. So what does that look like? Well, like we said here, it must be greater than or equal to 2. So 2 is our start. You got to make a pit stop at 3 because 3 is not a place where we can actually live for the x. So you're going to put the 3 right here. That's a parenthesis because it's on the bottom part of the fraction. It is a domain issue. Now here's the tricky part that's unique to this example. I'm actually not even going to include the 0 and negative 3. Because 0 and negative 3 live out here. 0's over here, negative 3's over here. They've basically been already ousted from the party before we even started writing it in interval notation. So I can just say go to infinity and you will encounter no more domain issues. Now you guys might get in trouble with this part because you're thinking to yourself, okay, I've got intervals, so now I got to test them. you're not testing the intervals on this one because you don't have an inequality in which you had to do quadratic stuff or had a fraction inside of it. I guess what I'm saying is the testing of the intervals are to solve the inequalities. I already solved it. So that's my answer, with a little union symbol in between. All right. Number 4. All right, what do we do if there's 2 roots? Well, the function has to be able to live where 16 minus x squared is greater than or equal to 0, and where 5x plus 4 is greater than or equal to 0. It's got to satisfy both of these parameters. So because there's no squares or fractions in this one, we can just get x by itself through traditional means. Subtract 4 from both sides, and divide by 5. Yeah. This one, not so traditional because of the square. So what I have to do is say, oh, what are my critical numbers? That's going to be 4 minus x, 4 plus x, which gives me plus or minus 4 for my critical numbers. It's not that they can't equal. Those are my critical numbers. So to figure out where this lives, I got to test these. So I got to go from negative infinity to negative 4, bracket, negative 4 to 4, also bracketed, and then 4 to infinity. So step 1, find your critical numbers. Step 2, make the interval. Step 3, test them. So negative 5, 0, 5 would be spots. So if I plugged it in here, negative 5 squared is 25. 16 minus 25. It's a negative number. You plug in 0, 16 minus 0 squared, that's positive. 5, also negative. So these two don't work. This one does. So here's what we're thinking. My function's got to live from negative 4 to 4, but it's also got to be greater than or equal to negative 4/5. So one way in which you guys can visualize this is to say, if I were to make a number line and I were to graph both solutions, so let's say I do this one in green, this would be the visual representation of my solutions. And I did this one in red. That'd be everybody bigger than negative 4/5. And it just keeps going forever in that direction. Where is the spot where both green and red coexist? Where do they both live? Well, together they live from here to there, which is going to be my final answer for the interval notation of domain. So you're going from negative 4/5 to 4. And that would be your solution. Yeah. By the way, did you guys remember that this is actually a very recognizable, it's almost like a celebrity equation. You can recognize it. That's a semicircle. So where do the x's for a semicircle live? Just in a very controlled place. This is a semicircle with radius 4. So you technically could have, you could have foregone this entire procedure and just said, that's a semicircle. It lives between the left radius and the right radius. Negative 4 to 4. Just throwing that out there. Again, another nice little graphing checkpoint for you. That's it. All right. I hope these videos were super helpful for you and you enjoyed them. They were clear, concise, and spot on. I got nothing more to say. Good luck. Thanks for watching.